Hello everyone, welcome back. Today I want to do a little bit of a different video. So I'm done covering content in chapter 1, which is basically kinematics. Next chapter will be on forces, Newton's laws. Still very basic stuff. This video is really just meant as a way for you to practice with a couple examples I came up with. You just make sure that you're comprehending everything at some, basic level. This is probably not going to be as hard as some of your university or like AP level stuff, but more I just want it to be, think about it just as a way to practice, get thinking in the right way. It's not the best, I know, I am sorry, but I really do hope this helps you start to think in a unique way, the way that a physicist thinks. Okay, so I want to start out with just some math practice here. So, what angle theta satisfies the magnitude of A cross B equals 2 times A dot B? Okay, the reason there's no magnitude there is because this will be a scalar, so we don't need to write magnitude. This will be a vector, but I'm going to make it a scalar with the magnitude. So the magnitude of A cross B, well, we can use our formula here. A cross B, the magnitude of that equals AB sine theta. Just as a side note, I really do recommend you try these problems on your own first, but I will show you how to work them out. So the other thing we can use here is that the magnitude of the dot product, in other words, A cross B, or sorry, A dot B. Jeez, I even said dot. Is equal to AB times the cosine of theta. All right? Well, now we can just go ahead and write this out like this. AB sine theta equals 2A times B cosine theta. Okay, what are we instantly noticing? We have an A and a B on this side, and A and B on this side. It does not matter what the magnitude of A and B is, so long as it is the same A and the same B on each side. Go ahead and cross these out, because we'll just divide either side by AB. Okay? And here's where we're going to get into the angle that satisfies this. We're going to say that the sine of this angle, theta, should be equal to 2 times the cosine of this angle, theta. All right, well, I already broke my lead. It's a good start. So what I can do here is I can divide either side by cosine theta. And sine theta over cosine theta equals tangent theta. So I guess we could add that to our formulas here. All right. So now I have tangent theta right here equals 2. Well, I can do something called taking the inverse tangent, or the arctangent, of either side. And I will get that theta equals the inverse, or arc, however you want to put it, tangent of 2. And really quickly, I will bring out my calculator. Sorry for the glare on the calculator, I know. But, I do have to have lights on to make this clear. So it's just going to be equal to the inverse tangent. I'll show you the buttons here, in case you have a calculator like this. Second tangent. Now I'm just going to press 2. Trust you know where that is. I can close my parentheses with this button. Doesn't really matter if I do or not, though. My calculator is in degree mode. I worried for a second I had it set in radian mode, but no. So we're going to see that it is 63.43 roughly. I'll change that to like a roughly 63.43 degrees. Okay. If you want to give an exact answer, give this. All right. Next up, this is going to be a 3D position, velocity, and acceleration vector. So right here we have r of t equals 3t in the x hat plus 2 in the y hat, and then minus, make that a little bit darker, minus the quantity 4t squared plus 2t minus 3 in the z hat. And I want to convert this to velocity and acceleration. Okay, well, here are the basic formulas I'm going to need. I'm going to need that the derivative of position, I'll rewrite that with an r. That is my bad. We are in 3 dimensions here. Thought I learned my lesson, but I didn't. About hitting the camera with the pencil. So this is going to be equal to velocity as a function of time and the derivative of velocity with respect to time equals the acceleration as a function of time. To note that they're vectors. I do that a lot. I will occasionally get lazy, and other physics teachers, not that I'm really a physics teacher, I'm just a guy who makes videos on the internet, but people who teach physics in a broad sense will kind of get lazy with the vector notation signs. It is what it is. So here we have that the velocity as it changes as a function of time, well, the derivative of 3t, this is basically just a power rule problem, by the way. There's no sines, cosines, anything, natural logs, nothing like that in here. So I'm just going to go ahead and write out the power rule in case you're not familiar with it. So the derivative with respect to x of x to the n is just equal to n times x to the n minus 1 power. Okay, and you'll see, if you don't understand this, you'll see it over here and it'll make sense. So this t right here is really to the first power. Okay, and I'm taking the derivative with respect to time, not with respect to x, but I always write my rules out that way, just because I'm trying to be very general. We will eventually start taking the derivatives with respect to other variables, and you'll see why I do this very generally when I write my rules out. Okay, so it's 1 up here. We would multiply this by 1. Well, 3 times 1 is just 3. And then the reason I don't write a t there is because t is to the first power. Subtract 1. Boom, that's 0. Anything to the 0th power is 1. I mean, I guess we could write that out. I don't know. I don't really know how much to write out. I try to write out more in case people aren't very comfortable with these topics. So the derivative of any constant is 0. You can use the power rule kind of to figure, well, I guess you can't, but because there's no x here, so it would just be like n. Derivative of n. I guess I could write that out. Derivative of n is 0. Okay. So this is just going to go away, basically. I won't even write it in because we're just adding 0. What's the point of that? Okay. Now here we have to be kind of careful. So I'm going to leave the minus outside for now. I might put it back in later. But so minus the quantity, 4t squared, says subtract 1 from the power, multiply the original power, 2, times that 4. We just get 8t. 2 minus 1 is 1. 8t, constant 0, so we can already cover that up, basically. And then we can do the same thing that we did here, over here. Minus 1 to the power, that's 1. 2 times 1 is 1. 8t plus 2. And that is going to be in the z hat direction. Now, if we want to find the acceleration as a function of time, we are going to have this 3 go away because it's a constant. And then we are just going to, we'll have that 2 go away as well because that's a constant. And then we'll just find that it's, well, the t's going to go away as well. And now that I realize that the t's going to go away as well, we'll just be left with 8 in the z hat, but it'll be minus 8 right there. And we will get minus 8 in the z hat. It's also important to note units. This is all in meters per second. This is in meters per second squared, which is equal to meters per second, the amount of velocity we gain per second. Or in this case, probably lose because it's negative. So we're deaccelerating, or just accelerating in the negative direction. However you want to look at that. Okay. And just so you know, if you wrote your velocity and you distributed this negative through and had a plus here, it's fine as long as it's plus negative 8t minus 2. As long as it's that, that's fine. But since I had to leave the parentheses in there anyway to multiply everything by the unit vector, I just thought I'd leave the negatives there. It's not a huge deal. Okay, there's that problem done. This one's going to be significantly more difficult. As for formulas here, it's going to be a lot more tricky. So here we have we have a toy car on a circular racetrack. I'm going to start there. And we want to know the average speed and average velocity over 3 laps. We'll assume it starts here and then makes 1, 2, 3 laps. It's a uniform circular motion. Okay? We'll have some angular velocity in this direction. Okay, here's our car, and it's racing along this racetrack. And the reason I put toy car is because this is not up to actual car speeds or measurements. Obviously, a car wouldn't race around a track that big. So just imagine like a Hot Wheel or something. So now what we can do is we can go ahead and say, okay, well, we have a constant angular acceleration. So we can find angular velocity to be the integral of angular acceleration with respect to time, which is just t, alpha t. And now, because that's alpha t, we're going to assume, because a car obviously starts at rest in a race, we are going to assume that angular velocity is 0, so we won't have to add a constant of integration there. And we'll have that. I don't plug in numbers until the end. That's another thing. When you're solving physics problems, plug in your numbers at the end. Leave everything in variables until the end. If it's looking for a number. Sometimes it's not even looking for a number, so don't even bother. Okay? This problem is looking for a number, though. But now we're going to have to think about this somewhat a little bit more logically. So if theta equals the integral of angular velocity with respect to time, we can say, again, we're going to assume this is our start line, so there's no initial theta, which means no constant of integration. And we're just going to do this 1/2 alpha t squared. And here we are just going to use the inverse of the power rule. I should mention this. This is the exact opposite of what we did with the power rule, because integration is the exact opposite of a derivative. Okay? I don't want to rewrite out those formulas because I'm going to be strapped for space. If you need to, just look it up or something. Okay. Now it's very, 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 very important to use radians here. Okay? I guess you could say these are our formulas. We don't really need that many formulas for this problem, but I guess you could say those are our formulas. I just kind of wrote them off to the side so I could give myself a little bit more room in the center. So if we go 1 lap all the way around, well, this is 0 radians, this is pi radians, this is 2 pi radians, right? So 1 rotation around this circle, we go 2 pi radians. Okay? And I leave the unit off because radians are unitless. 2 laps, you might see where this is going, 4 pi. 3 laps, just got my hair caught. 3 laps, is 6 pi. Okay. We have theta with acceleration and time. Okay. So we want as part of finding average speed and average velocity, we need time. So if we could solve for time here, that'd be very useful. So let's go ahead and do that. So we can say that 6 pi equals 1/2 alpha times t squared. Okay, multiplied either side by 2. I'm going to switch the way I'm writing this just so we can solve for t. And then divide by alpha. The square root of that is t. I wouldn't blame you if you plugged in numbers here. It's really not a big deal if you did, but I'm going to write it like that. Okay. Next up, if we want to find speed, well, speed, which I'm just going to write with an S, equals distance over the time. Okay, so really quickly here, one formula that we are going to need is the circumference, which equals 2 pi times the radius of the circle. All right, you might have that already memorized. In case you don't, boom, there it is. But we're not just traveling the circumference of the circle. The circumference will be our part of our distance, but we're going around 3 times because we're doing 3 whole laps. So multiply this by 3, and that's going to be equal to our distance, which in this case will be equal to 6 pi r. All right, now we can go ahead and write 6 pi r all over the square root of 12 pi over alpha. That's going to be equal to our speed, s. Plugging in some numbers here, now is when I recommend you do this. We get 6 times 0.5 times pi all over. So here we're going to plug in a 0.5 on the bottom. If we divide by half, we're really multiplying by 2. So it's just going to be over the square root of 24 pi. Okay, and we get 3 pi. Really, that's 3, so now we get 3 pi over the square root of 24 pi. Do what math you can in your head, but do not do anything more than what you're comfortable with. I'm comfortable with saying 6 times a half is 3, but I do recommend you go ahead and plug in here. So we're going to take 3 second pi. So 3 pi over the square root of 24 pi. That's some loud thunder. That's what living in the Midwest is like, in case you don't live in the Midwest of the United States. Okay, we get, I'm going to call that 1.09 meters per second. Again, it's an approximation, but, you know. Boom. There's that done. Sorry, the calculator's like awkwardly on the edge of the screen. But there's our average speed, but we also need average velocity. Here's the funny part of this. So distance is scalar, okay? Distance, how you travel. For example, if I walk forward a meter and then back a meter, my distance that I've walked is 2 meters. But velocity, that's a vector, and that's based on displacement. Displacement is defined as R2 minus R1. Okay, well, let's find R2. Well, we go around 3 times. We're there. What's R1? Well, we're right here. Same thing as the start line, because the start line is also the end line in this case. I'm not going to do like half a lap. That's just weird. I don't like that. End in the place you start. We can say this is just going to be equal to 0. Any number minus itself, I mean, that just has to be 0. You wouldn't even have to do this if I just asked for average velocity, because it doesn't even matter what time is, right? That little V bar means like average. So that's just equal to the change in R over the change in time. It's 0 over, let's say we don't know time. I mean, we do, but let's say we don't. Doesn't matter. Boom. 0 meters per second. There's a little conceptual problem for you. That circling was horrible. But I'm kind of trying to work around my camera, so I apologize. Okay, that is going to do it for this video. I really hope you got something from this. If nothing else, I hope this made you start to think in a way that a physicist would think when they're approaching this problem. Okay? Well, I hope these problems helped you. The next video will be a little bit more lighthearted. I kind of want to do a little bit of more like of applied physics. You'll see. In case it's not already up and uploaded, you'll see. But anyway, I hope you enjoyed this video. I hope it was helpful to you. Have a good day, night, afternoon, whatever, wherever you are, whatever time. I'll see you in the next video, hopefully. See ya.